Cool, the recording started. We're gonna build the CPU today. Cool. So, not the CPU, just the ALU. So, okay, let's start by figuring out iVerilog. So let's go here. So I have this counter.verilog, right? So it's a module with an output, a clock, and a reset. It has a parameter, so it has the width. It has the output, which is out, so the variable of out. And its input is clock and reset. So you have all of these, and these are like your pins on the end of it. And so you have out and clock and reset. So register, so you have a register that stores out, so it's width -1 to 0. Oh, 7 to 0, yeah, makes sense. And a wire coming in, which is clock and reset. And so always, if we see a positive edge on the clock or a positive edge on reset, if reset's on, we set the output to 0. Otherwise, we set the output to output +1 and end. Okay, that makes sense. That makes sense. And then counter tb.v. And so this is a testing thing. So register reset. And so at the beginning we go 17, 11, 29, 11. Oh, 17 cycles and a reset, 11 cycles and a reset, 29 cycles and a reset, 11 cycles and a reset. Cool. Always we set up a clock. Okay, cool. So that's our testing framework. Hello there, Mr. David JYLU7. This is a good evening. This is a good evening indeed. We are going to be designing an ALU today, and it should be able to add 2 numbers in the RISC-V style, which is what we're going to try to do. So, yes. So I'm going to copy over the counter, and I'm going to call it, I don't know, ALU.v. I'll call it adder.v. Now I'll call it ALU.v, and we'll just like split it up into different modules as is. And I'm going to copy over counter tb.v into ALU testing binary.v. Then I'm going to copy over file list to ALU file list.txt and ALU file list.txt, and then ALU.v, ALU.tb.v. Cool. So there we go. Now we gotta figure out how to compile this stuff. So let's go here. Let's go to the iVerilog, right? Let's go to the iVerilog and compilation. How do I compile? Getting started with Icarus Verilog. Yes. Compile with the file list. Yep. Okay. Cool. And so nvim compile.sh. Gonna paste that in. That's so my design. Sure, I'll call it my design. And then we're gonna plus x compile.sh /compile.sh, and then vvp my design. Yep. Exit. Quit. Finish. Cool. Finish is what it is. Okay. Yeah, so it runs, and there we go. We have a testing framework. We have all of that, which is very good. Very nice, actually. This is a great success. So, I'm going to make that a little bit bigger. Cool. So now what we have to do from here is we got to get to work on the ALU. So, no, let's do nvim test.sh. Cool, and then I'm just going to copy over this command, chmod plus x test.sh. Not underscore x plus x. And then /test.sh. Cool. Finish. Amazing. So let's work on a testing thing first, right? So nvim tests thing. So obviously we only have the ALU run on the clock, right? This is very important. So we only have the ALU run on the clock. So cool. Now what we need to do is, yes, we have to keep doing this. So hold on, what am I doing? Yeah, so we have a clock. Initial begin, and so counter C1 is value clock. So we have the counter, and so we monitor at time this value is this, time value value. Huh? Okay, dollar monitor, I don't know. So we have register reset. We feed reset into here. What do these numbers mean? Make a reset that pulses once. On, off, on, off. Okay, sure. We're just testing all this stuff individually. Cool. So, I like the regular pulsing clock. right? This is very useful. Hold on. nvim alu.v. Let me rename this to alu. ALU. Output is going to be 8. We're obviously going to have the clock. And so we have output. We're going to have input data. Input data. Input data A. Input data B, right? Because we have 2 inputs to this ALU. And then we have opcode and out. Cool. So parameter width 8. Let's set it 32. Because this is RISC-V. We do stuff in RISC-V world, right? So 32-bit width, right? So, cool. So output is going to be out. Sure. I'll call it output. I'm calling other stuff input. This is an output, right? Output is output. Input is literally everything else. It's going to be clock. It's going to be... No, well... Hold on. Input, and then with -1 to 0, it's going to be input data A, input data B, and our opcode, right? Cool. And so we have a register for our output. Also, this is not saying a variable, that is output. And a wire for clock and reset. What does register and wire do? Keywords. The keywords, yup. To attach the full case. Hold on. The following shows how to attach attributes of case statement. Case foo, rest of the case statement. Full case equals 1. Case foo, or what? Huh? Okay, hold on. I don't actually understand Verilog, so this is a thing I have to figure out live. I have to figure out Verilog live. Amazing. Cool. So, we only care... So, if positive edge on the clock... screw it. Let's set up a register for the input data and whatnot. So, if... opcode equals what is the opcode for an add in RISC-V? Add opcode 0110011. Cool. RS1. These come from registers. Where is add immediate? Right. Has to come from registers. I don't care about that right now. So what we're gonna do is we're gonna keep going. We're just gonna keep going. Opcode equals 0110011. Cool. That's going to be a number. I'll do 0b. Hold on. What is the value set? 0 is a 0, 1 is a 1, x is unknown, z is a high impedance state. Yup. Syntax for variable declaration. Oh. Register. Okay, you have variables. Vectored, net, scalar, vectored. Okay, sure. 2 types of strength. Okay, I don't actually. Hold on. Gate and switch level modeling. How do I check equality? I just need to have like a very nice equality switch, you know? Just like a, hey, we have this thing, check to see if 2 things are equal, right? You know what? I think what we're going to do, you know what? If opcode, well, let's go back to RISC-V code, is 011, right? I'll just convert this to a number. So that's 3, 8, 16. So that's 19 plus 32 is 19 plus 32, 51. Cool. So obviously, if opcode is 51, out is going to be input data A plus input data B. Obviously, I'm not actually creating any of the adding circuits here, but you know, it is what it is. Else out is 0. Let's just set it to 0 for ease of use. Cool. And so this only applies on the positive edge of the clock. And this should just work. So if I go back in here, So it's going to, instead of being a counter, it's going to be ALU. The input values, hold on. So monitor the value. Okay, so wire 70 value. So this is going to be our output, right? Hold on. Let's go pull it up. Hold on. I'll make this a lot bigger so it's visible on stream. Mounted space, chip design, right? So we have chip design. And so what we're going to do here, nvim alu.v. Cool. So we have the format here, ALU. So we have our input data. And so our input data is going to, obviously we have, okay, hold on. Let's just set up a register with our input data. So it's going to be, I don't know. It's going to be, well, obviously I have to set a width. Parameter width is 32 because it's a 32-bit thing. We're gonna build a 32-bit CPU and then we're gonna go up to 64-bit. So register width -1 colon 0. Right, so we're gonna set up a quick register that we do stuff in. And so I'm gonna call this input A. And so initial begin 1, 2, 3, 4, and obviously sure at 100 let's stop. And so I'll set input A to be, let's just do 1, 2. Let's just edit that. So 2, 3, 4, and input A is going to be 2, 3, 4. Cool. And then let's just have it go until 100 to stop. And then let's copy that and let's paste it down here. Cool. And so this is going to be input B. And let's just add numbers up 2 at a time, right? As you do. Cool. So you have input B as the 2 registers. You have the clock that's always ticking. Cool. Always just tick the clock. I should probably increase. Whatever. I'll leave it as is and see what happens, right? Cool. And so then input output, you have opcode. So then reg. I'll just yoink this. Wait, hold on. How big? Yeah, let's just opcode to be 32 bits as well. Why not? Why not? I know it's not technically 32 bits because we have all the other stuff, but you know, let's just set opcode to be 32 bits. Cool. So we have a opcode in the register, and then we have value, which is our output. So I'll set this to be, again, width -1, and it's going to be our output. Cool. And so from here, we're gonna output, and here output, and I'll just set this to be output. Monitor it. Yup. ALU. Now we set in all of our values. So we're gonna go input A, input B, the opcode, and then the output, which is going to be output. Then I'll clock, and we don't have a reset because it is whatever. Right? Cool. And there we go. Now what we have to do is, I don't know, let's run it. /compile, /test. At time 0. Finish. What's going on here? Value at time 0, 17, 35, 1, 2, 3, 0, 1, 2, 3, 4. This is just with the old thing. Hold on. nvim compile sh. File list. No. We have to use the ALU file list. Well, what did I call it? It's called ALU file list. Yep. ALU file list. That /compile dot. Oh, cannot open file ALU file list .txt. Compile. There we go. We have a whole bunch of errors. Cool. So ALU.v, one syntax error. So v module ALU. What is the syntax error here? Error in port declaration. Invalid module. Okay, so the module is bad. in 5 and 9. 5. Output with output and 9. Register output. Oh, I'm using a variable I'm not using. Output. Probably good to fix that. Compile. We have more errors. Can we just not use output? Hold on. Let me rename this to out. And let's see if this works. This is going to be unfortunate if this is the case, but, you know, let's find out. That was, in fact, the case. Cool. ALU test underscore test bench. Cool. So let's rename this from output to out. And instead of output, out. Out. And here is going to be out. Cool. Let's come out. Port of module declared as input and as regular type. So ALU nvim ALU.v. Cool. So it's input and register, which cannot be case. So let's comment this. Hold on. Is it these for comments? Yeah. Okay. So let's comment that out. Compile it. Cool. /test. Cool. 0 and 5. Huh. At time 0, 5, output is this. Huh. So we have the ALU. And Vim. Oh, because we don't actually set the opcode. Whoopsies. So hold on. Let me set these numbers to be higher. So I'll set this to 2, 3, 4, 5. 2, 3, 4, 5. And then here we have the clock. And then here, initial begin. What? Hashtag at time step 1. Opcode equals 51. End. Cool. And so then let's finish. /compile. /test. 0, 4, 8. I mean, that's pretty good. Time 5, 15. nvim ALUTB. Okay, wait, what sets the... Wait, how are we printing the timeout actually here? At time, %sign T, oh, $time. Output equals %sign H and then %sign 0D, right? Cool. So then let's set these numbers to be bigger. So I don't know, let's go, hold on, let's go 10, 20, 30, 30, 40, and then same for here. 10, 20, 30, 40, 40. Cool. Clock always is just the opposite. Oh, I can just set this to be equal. Equals. No. If I want to be able to test different things, yeah. /compile, /test. Cool. So there we go. We're going 2, 4, 6, 8 at time 15, 35, 65, 105, 20, 30, 40. Oh, that's time in between. Ah, okay, that checks out. So hold on. These should all just be 10. No. Ones. These should all just be ones. Yes. And so then there we go. Oh, hold on. I forgot to compile it. Cool. And then it just edits at 5. Okay, because... Hold on. What is going on with our test framework? Initial. Monitor this. At time this. Output is this. Okay, so maybe 1 is too small. Maybe I have to set this to 2. So that the clock actually has time to do stuff. And this one's opcode is... Yeah, so we're skipping the first one, only printing the second one. Compile. Test. 0, 5, 15, 4, 8. Okay, I have no clue what's going on here. I'll just set this timer to be 10, and then we'll fix it later, because I think this is just a testing code. 10, 10, 10, 10, 10, 10, 10, 10. Cool. /compile, /test. Yeah, okay, so that's what first 5 5 cycles, we do whatever. But yeah, so we go 2, 4, 6, 8. Cool. So we have ALU.v. Cool. So we have this, right? So I'm just gonna calmly delete this now. Cool. So out is input data A plus B if opcode is 51. Yeah, so hold on. Let's go back to the RISC-V code. What are all of the... Hold on. So this is the RISC-V base instructions, integer computational instructions, integer register immediate instructions. Right, so that's for I format instructions. That's not what we're going to be working on. Base instruction formats. R type, I type, S type, U type. Okay. I know these. I literally took a course on this at university. So yeah, that's something I have to figure out. Yeah, integer computational instructions, add, shift. Cool. Jump in, link register. Okay, how do I... You know what we're gonna do? You know what we're gonna do here? We're gonna do subtraction here as well. So, how do I do else if? Elif? Else? If. Else space if and... I can just type else if, and then I do my thing. Opcode is... And so the opcode for subtraction is the exact same as addition. What is... right. Oh, the opcode tells us which set this is. Okay, cool. So we want func7. And... yeah, we want func7. Okay, hold on. We need more inputs here. I'll call this... Instead of opcode, I'll call this func... funct7. And then here, instead of opcode, I'll call it funct7. And then down here, I'll call it func7. And so instead of 51, if this is OX20, so that'd be 32. No, this would be 0. If this is 32, and not opcode, it's funct7. We're going to say out is input data minus that. Yep. Cool. 32. We also need func3 as an input. So let's go a nice func3 and a func7. And let's throw that in here as well. And func3. Obviously, this is taking up way too much width, but that's whatever. Func3, func7. I don't know. Let's also add a... No, let's leave this as is, and let's just have this keep going, right? Let's just test this thing with func3 and func7 now. So nvim alu testbench.v. So you have the width, the input, and so not opcode. Func3, which you're going to be editing. No, func3 equals 0. We're going to be editing func7. Yep. And so there we go. It should begin. And so func7. I don't know. Let's have it at... So at the start, hold on. At 0, funct... Hold on. Let's set it up as a default value. Right. So default value is going to be 0. And hold on. Let's just have it go... Have this cycle through... this, right? And just have it cycle through 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. We should probably have it be different numbers. So 4, 3, 2, 1. Right? Cool. 1, 2, 3, 4. And then that one's 4, 3, 2, 1. Func7 is 0. And at time 50, I should probably set this one. That should not be A. This should be B. Cool. And so, yeah. And so, let's say up here, I don't know, I'll set this one to have a, I don't know, let's set it have a 20-second delay. And this one should also have the same 20-second delay. Cool. And so then down here, what we have to do is we have a func7. And we just have to keep, yeah, so 50 seconds in, func7 goes to 32. And so instead of opcode, we're going to go with a very nice func3 and func7. Cool. So compile, test. 2, 4, 6, 8, and then we subtract 4. 4 from 4 is 0. Minus 2. What? Wait, hold on. 2, 4, 6, 8. At 55 is when the other things changes, right? So the opcode changes. What's the difference between iVerilog? iVerilog is just an implementation of Verilog, right? So basically, okay, I think you've probably left at this point. But iVerilog is just an implementation of Verilog. It's an Icarus Verilog. So this guy, Icarus, he made this Verilog. Yeah. Cool. So, yeah. Hold on. What am I? I did A minus B. So I went 1, 2, 3, 4. 1 minus 4 here. So this would be D, E, F. Yes. So that's minus 3, minus 1, 1, 3. Yeah, no, that checks out. And this is when the opcode changes to subtraction and our inputs are what they are. Cool. Now I have to figure out the fastest I can change this around. Right? So instead of this, let's just remove a 0 from all of these. Including the stop. Why not? And let's just remove a 0 from all of these. And instead of 50, let's change it to 5. How fast... finish. Hold on. How does the clock work? Because obviously a 10 works just fine. Why do we have a 5-second thing at the start anyways? What is going on there? Always. Oh, starting from 5 is when the clock does things. A clock cycle is 5. No, a clock cycle is 1. 1, 3, 5, 7. Okay, you know what? I can work with that. I can work with that. We do everything on even numbers. So then this must be at... yeah, so this, I had to change this all to 2. This is a 4. 2, 2, 2. Whatever, 10 is whatever. 2, 2, 2, 2. This one's a 4. 2, 2, 2. Yeah, I don't care about the 10. 5. No, this is a 10. And the clock is clocking. Cool, yes. 2, 4, 6, 8, 0, because we set we changed it to subtraction. Negative, negative, negative. Cool. There we go. This is a very simple thing, all things considered, right? Very simple thing, considering everything. So, yeah. So now what we have to do is stop at 28. That checks out, plus 10. And Vim. V. Cool. So now what we have to do is we have to... I'm going to make up a really simple... Okay, hold on. Let me diagram this. Let me go to draw.io. Come on. Load faster. Device, sure. Create new diagram. Blank diagram. Sure. Put in my documents. Cool. I don't care. Hello? Okay, cool. They changed their UI on this. This is new. Okay, cool, whatever. So, basically, we're going to be doing our stuff. So, we have our ALU here. I want to make a really simple test bed, right? So, we're going to have all of our registers here. We're going to do our instruction decode. So, obviously, we're going to have our registers here. And then we're going to have our, I don't know, instructions here. And we're going to do our instruction decode here, right? So we're going to feed in the instructions. We're going to feed in the registers. We're going to decode the instruction. And then we're going to feed the registers into our ALU. And we're not going to put registers there. We're going to decode our instruction there. And then we're going to feed this information into our ALU that we then put back into the registers. How do I... There we go. This should be a... like that. Yes! There we go. Cool. So, we're just going to do a little bit of this. And I'm going to have, I don't know, we're going to pin on this as our output, right? So, yes. And then we're just going to set the instructions to be the instructions. So, yeah. Amazing. So, what I'm just going to nvim, I don't know, cpu.v, right? So the CPU, let's just yoink all of this in, nvim cpu.v, and I'm gonna call this CPU, obviously. And so the CPU is going to have it's going to take in the clock, it's going to have an output, and it's going to take in an instruction, a 32-bit instruction. So the width is yep, you have an output, and then from here, what we're going to do is our input is going to be instruction. Cool, and we have a parameter. Width out is instruction, input, and a register for the output, yep. And then obviously wire for the clock, yep. And so on the positive thing of the clock, hold on. And now we're going to need ALU. We're going to need an instruction decode step that takes it. Well, let me undo that. Out is 0. Cool. nvim ALU. Let's move ALU file list. mv ALU file list to. I'm gonna move it over to CPU file list.txt, and then I'm gonna go into that. CPU underscore file list.txt. I'll add CPU.v. I'll rename ALUTB to CPU testbench, and then CPU testbench dot. I'll have to move the ALU one. Move ALU testbench to CPU testbench.v. Cool. Now let me get into the CPU testbench.v. Cool. So let's just set up a few instructions, right? So we're going to have, what instruction are we going to have? We're going to have a load immediate, right? So we're just going to be able to write like, load immediate is not a real thing. It's going to be an add with x0. So hold on, let's manually generate that, right? So it's going to be an add immediate with x0, right? And so obviously x0, because we know RISC-V, it connects directly to 0. So we're going to have the, yeah, okay, let's just slowly work our way up there, right? So we're going to set up all the parts of our, and then hold on, let's go back here. And let me zoom out a bit. Cool. There we go. Instructions are going to just feed in there. We're not going to have instruction cache or whatever. I'm going to have this. Where is the send to back button now? Hold on, let's reset the zoom. That doesn't help me at all. Okay. And it just makes it worse on stream. Okay, we're going to zoom in. Okay, we can't zoom. Yes, we can zoom in on stream. Cool. So, is this sent back? No. Where is this? Arrange? Send backwards. Yes. Cool. There we go. So this is going to be our, this is going to be our CPU, but I need to send it to the top. How do I send it to the top now? What have they done with my software? Whatever. This is just going to be a CPU, right? So we're going to have an instructions just come in. For now, instruction decode registers ALU. So nvim instruction decode dot v, and then nvim cpu tb dot v, not testbench. Nvim, we're just going to get the cpu dot v. Cool. Let's yoink it all down. Hold on. Cool. And then we're going to go into our instruction decode. Paste it in. And so it's just going to be an instruction and an output. No clock signal here. And then, you know what? Now let's keep the clock signal, because I like the clock signal, making sure everything just works. You know, I like the clock signal. It's very nice. So, yeah. What I need to do is, yeah. So what I need to do is just figure out how this all works. Yeah, so this is just a continue figuring it out type beat, right? So yeah. So I just had to, yeah, okay. So This is instruction decode module. I'm just gonna have it go on a CPU because that just makes it easier. Instruction decode. And hold on, let me nvim the CPU file list. And then this is going to be add. I should probably put this in order. Instruction decode dot v. Yeah, that's whatever. I don't particularly care. Cool. So now we have instruction decode dot v. So we have our output, which is out. Our input is instruction. We have a clock. And so, cool. So, we don't have one output here. We're going to have multiple. Step one is we're going to have a... Step one is obviously we're going to have funct7 and funct... hold on, I should put funct3 before funct7. Funct3, funct7. Next, what we're going to have is... yeah, so we're going to have funct3, funct7. We're going to have rs1, rs2. Hold on, let's go back to the RISC-V card for iFormat. rs1, rs2, rd, destination register, very important. And the opcode. Cool. So obviously we're going to ignore opcode for now. And what we're going to... So output is going to be funct3, funct funct7, then rs1, rs2, rd, and the opcode, right? Cool. Setting those up as output. We said all of them are 32 bits wide because I don't want to deal with sizing right now. I probably should, but I don't want to deal with it. And then obviously, always the positive edge of the clock. We're gonna set. Yeah, so I'm gonna assume. Well, I should probably do with the R format versus I format versus whatever, right? So that's probably a useful thing to do, right? Let's be real here. But okay, so first step one, let's get the opcode, right? So opcode is going to be the instruction of, and so it's going to be 0:6 because that's 7 bits. Then the what's up next? RD. Destination register. Obviously, we should probably be looking at what opcode is before we do some of this stuff, but, you know, whatever. RD is going to be 7 to 11. Because here's the thing. We only support our format right now, okay? We will support the other formats soon, but we only support our format. RD is an actual thing they use. I'll just use reg dest destination register. Yeah. Cool. Instead of RD, it's going to be dest reg. Dest reg. Cool. Then down here, what we're going to do is dest reg. How is this? Oh, hold on. I probably put an end down here. Okay, I'll leave it as RD. Cool. Huh? Go back to the counter.v. Let's figure out how they did this. Always it and in the tab if else. Okay. Cool. Whatever. I don't care enough if it fails. We fix it when it fails. Then we find funct3, and it's 12 to 14. Then rs1, which is going to be our source register. So this is going to be instruction 15 to 19. 15 to 19. rs2 is going to be 20 to 24. 20 to 24. rs2. And then funct7, that's going to be instruction of 25 to 31. 25 to 31. Cool. Why are all of these things okay, whatever, we leave it as is. And then there we go. Cool. CPU.v. So we have a CPU with our width and our instruction. And so in here, I'm going to have an instruction decode, I'll call it ID for instruction decode. And so the input is going to be instruction. And then I should probably, hold on. Let's just yoink all of that. And then let's go down here and let's set up registers for all of them, right? Register for, that is of size width -1:0. And that's just going to be all of this except the clock and all of the other nonsense that we have here. Cool. And then we have a func3 and func7. So we have instruction. Then we go func3, func7, rs1, rs2. The destination register, I call it OD. It's OD. I should probably fix that in there, in the actual thing. OD, the opcode, and the clock. See, okay, a good friend, the clock. Cool. And so then we have instruction decode, and the output, I don't know, I'll just output, I'll just test our instruction decode real quick. So I'll just output, I don't know, our opcode. I'll output our opcode. Cool. And so then CPU test bench, input A, I should probably rename these. So, well, we only have one input, which is our instruction. Instruction to instruction is, I don't know, let's just set up is like 15. And let's just leave it at, I don't know, 15 is our instruction. And so we should just get 15 on the output, and we'll go from there, right? So, yeah, func3, func7, whatever, regular pulsing clock. The wire for output. Does CPU have? Yeah, CPU has an output. And then obviously we're going to have our CPU that takes in our instruction and out and the clock. Instruction, out, and the clock. And so then compile it. Cannot open. Oh. Compile .sh. And so that ALU, this is going to be a CPU, right? Let's compile. Error in instruction decode. Invalid initialization. Cool, this is good to know. 14, 15, 16, 17, 18. 14, 15, 16, 17, 18. Okay, so invalid initialization. I don't know, let's... Sure, that checks out. Let's compile. Ah, there we go. So you can, opcode is not a valid L value, and that opcode here is declared here as wire. Huh? Is it? No, it's an output. Oh, no. Oh, we don't have registers for all of these. Okay. Let's just yoink this, paste it down here, and just call it registers. Instruction error, it's out of order. Huh? Oh wait, hold on, I forgot to rename it. Whoopsies. This should be RD. We are stuck doing all of this. Cool. Part select instruction is out of order. Okay, do I do 6 to 0? Big to small? Yes, I do. Okay, cool. So then this is 11 to 7. This is 14 to 12. This is 19 to 15. This is 24 to 20. This is 31 to 25. Hold on, yeah, 31 to 25. No issues there. The rest of it is CPU. 13. Func3 cannot be driven by primitives or whatever. So then 13. Func3 cannot be driven. Why can Func3 not be driven? Because we have it set up as a register here. Func3 cannot be driven by primitives or continuous assignment. Does this apply to opcode? Yes. Output port expression must support continuous assignment. Opcode is connected to opcode. So why does it not support continuous assignment? We have a nice register here. Huh? It's a register with a nice width. It's going very well, you know. What? Register does not support continuous assignment is strange. Very strange. Right? So, how do we do this? Yeah. How do I figure this out? Okay, so we have out always at the positive edge of the clock. Out is the opcode. Why do the registers, why are they not assignable? Okay, hold on. Instead of opcode here, because I mean we just have the connection output, so set this to, hold on, no. Hold on, let's comment this out and let's see what errors we get. Yes, port 2 expects 32 bits, got 1. Padding ports, those are all warnings. Huh? Instruction deep code expects 32 bits, got 1. Sure. And then what's the problem with the testing? 1, 1, 5 outputs 1. Okay, I think this is just broken right now because we're only feeding it 1, right? So that's the problem. Cool. These registers must have proper width. Yes, but we also have to be able to write to them. Okay, hold on. Let's pull up in Verilog. Search for continuous assignments in which, so Verilog is primitives, it's the mixing of abstract, yep, continuous assignments. Yes. Continuous assignments. Yep. Assignments, continuous assignments, 68. Procedural, I don't want to do procedural, let's just go to page 68. 68, continuous assignments. Declaration colon equals continuous assignment is assign. List of assignments. What? Continuous drive values onto nets. This assignment shall occur whether the value on the right hand. Yep, this is good. Continuous assignments provide a way for the model. How do I set it? For example, the following is a net declaration form of the assignment. Yep, because it can be declared only once. Okay. How do I do continuous assignments in CPU test bench? It's reg with instruction. Okay, sure. Wire is for continuous. That checks out. So these aren't registers, these are wires. Cool. And so obviously we only edit output on the clock. / compile, / test. 3, 5. Huh? Okay. Hold on. CPU testbench.v. So instruction is just 15, so we should just get F as the output. I should probably fill in the full instruction. Yeah. Should probably fill one out. So that I can test all of this. Yeah, okay. Hold on, how do I 0D? I'll just do 0B 1111. No, I have to compile that first. Process compile syntax error. Malform statement. Yes. 0D. Okay. One. Oh, hold on. I have to set these. No, this is 2. This is good. 2. We're good. We're good. We're chilling. I don't know. 27. / compile. / test. 3, 5, 7. Why are we skipping the first one? Oh, because 3 is random, then 27, 15. Okay, why are we waiting until we actually start doing anything. 1 and then 27, 15, 15, 15. Yeah, what's the wait for? Do we have delays? No, clock gets at the 1, and universal clock for all of them. We probably have some delay nonsense going on here. Okay, whatever. 15, 32, 64. Let's just do that. 3, 5, 7, 9, 11. Okay, this does work. Okay. Strange, but it does work. We are chilling here where it does actually work. Okay, cool. So, yeah, okay, that's kind of strange actually. So we just have to have it keep doing this type of stuff, right? So 3, 5, 7, 9, 11, and 27, 15, 32, 64. Yeah. Okay, this all checks out. But why the extra 1 unit of delay? Is it the fact that output is a register instead of a wire? So let me set it to wire. Out is not declared here as a wire. Okay, hold on. Let me comment out the output because that's just the output. Out is not a valid L value. Why does it have to be? Because we just have it as. Oh, hold on. Where's the error? CPU.v5 is declared there as a wire. Okay, so it has to be a wire because we have it as the output. Okay, cool. Sure. You got it, boss. Wire output, yes. So it has to be a register? Yeah, okay, sure. And that's probably where our stuff comes because we only see it when the clock shifts down. So when it shifts up, we edit the values, and when it shifts down, we write it to the output. Yeah, that makes sense. That all makes sense, I think. Cool. And so we have a CPU. In here, we're gonna have we're gonna have a registers, right? Let's have, I don't know, let's have like 5 registers, right? We're gonna have, I'll set it down here. Registers, 32-bit registers. So with -1 colon 0. And so obviously these registers, how much of them will we have? Well, what is it? We have x0. Obviously, that's always going to be 0, right? We're going to have x1, x2, x3. We're going to have 4 registers right now at the start, right? This is going to be great success. I should probably make a registers file thing that actually has the registers and whatnot. Yes. CPU.v to registers.v. And so I'll call it, instead of CPU, I'll call it registers. And we're going to obviously keep the clock because clock is very nice. I like clock. Clock is very nice. I love clock. Clock is my favorite. Yeah. So now what? Yes. Now what I just have to do is I have to keep going here. So yeah. So in essence, we're gonna have out instruction clause. Yes. So registers. We're gonna have the output. We need multiple outputs. Out A, out B, and we're gonna have reg A, reg B, register A, register B, then write, right? So register write, register, and then in write. Yep, cool. So out instruct, and so output is out A and out B, and obviously I should probably also have out W because this is the information that we just wrote. Probably useful. I don't know. Out A, out B, out W. Cool. Input is going to be register A, register B, and register W, right? Because we're writing to it. And obviously also the in W, right? Because we're writing to it. We need to figure out what it's in. Cool. Then from here, we obviously have an input clock, and we also have to have a write enable. Write enable. I'll call it its full name. Write enable. Cool. Input clock and write enable. Cool. So we have a out as the register. We need out A, out B, out W as our registers. Wires, we have the clock, and we have write enable. Cool. And then for wires, these are our outputs, right? So we're gonna have. Hold on. So these registers are our outputs. These are going to be our. These are going to be our. Is for CPU. These are just going to be just wires in the thing, and so these are going to be just random wires. We don't have random wires. Let's just have 4 registers, right? So if. So we're gonna have a nice if here. So on. Reg A is 0. I don't need x0 as a thing here. I'm just going to output 0. If reg A is 0, out A equals out A, we're going to write into it a 0. If reg A is 1, I should probably do else if reg A is 1, out A is going to be whatever is the next one. And I'll just do this 2 more times. Paste, paste. 2, 2, 3, 3. Cool. Then I need to copy this for B. Hold on, let me delete that. And yep, paste that in there. And I'm just going to replace this with B. Cool. Capital B. Replace capital B. Replace capital B. And yeah, we're just going to repeat this. We're just going to write to here. And here as well. Cool. So we obviously have register A, register B. And then we also need the writing, right? And so obviously on positive edge of clock and positive and so we're going to have nested ifs here. If write enable is 0. Also, if it's 1, we're just gonna not have any. We're not gonna do anything on else. If write enable is 1, then what we do is we have a sub if, and then we're going to do reg W, because that's the register we're doing. Reg W is 1, then we set the value in x1 to be equal to the value in the data in W. I'll set it as data write. Right, yes. As data write. And I'll just yoink it, paste it, set it to an else for same for reg 2. And reg 3. And you know, we don't need an output write. We can safely get rid of that because you know what you're writing, you know? Cool. So we obviously have not in W, data W, yes. Cool, there we go. So we have our registers that should theoretically work. I should add it to our CPU file list, and I'll throw it in here. Registers.v. Cool. And it's just called registers. So nvim cpu.v. And in here, I will set up registers. And so these registers, regs, I don't know. The input to these, I'll delete this. the input to these registers. So hold on, I need to. Hold on, I'm gonna zoom this in for you guys. Of course, of course. See, mounted space, chip design, and then nvim registers.v. Cool. I should probably have individual test files for all of these, but that's whatever. We'll deal with it later. So reg A is going to be rs1. Reg B is going to be source register 2. Out A is and I'll set up a wire. Wire val A. Okay, the size is obviously width -1 colon 0. So val A, val B, and right val. I should do val right. Val right. Then we have. So we have the values of all of those. So rs1, rs2. Out A is val A, val B. Yes, and then we also need RD. Yep, RD is our destination register, and value to write is there. Write enable is. I'll just set write enable. I'll just set that as another wire. Write. I'll just set it to 1. Honestly, let's just set it to 1. We're always going to be writing. Whatever, I don't care. Write enable is going to be 1. Yup. And then our clock is going to be a very nice CLK. Cool. And then always on the output, out is going to be our, I don't know. I should probably throw in the ALU. ALU al. And so what does the ALU take? nvim ALU.v. So it takes in input data v. So it's going to take val A, val B, funct 3, funct 7. Output of the ALU is. I'm just going to connect that directly to out. Whoa, what's stopping me? Woof. No, I can't connect to that. That has to be connected to RD. It's going to be RD and CLK, not RD. It's connected to val. It's connected to val right. Because I guess all of our instructions here are write back instructions, right? So we have to just kind of keep doing that. Cool. And so, yeah, we just had to keep. I mean, yeah, we were pretty close here. And so the output, I don't know. I'll just set that as val right. I don't know. Cool. So we have all of this. Now we have to edit testing. So nvim, not test, CPU tb.v. Cool. Cool. So what is the? Well, we don't have add immediate yet. Okay, that's probably useful to have an add immediate. Yeah. Cool. Yeah. So I probably have an add immediate at some point in here. So yeah. Huh. Hold on, I'm losing. Okay. I am slightly losing my mind. Yeah, okay, hold on. Yes. Cool. So we have func 3, func 7, rs1, R type. We should probably add I type support. Yes. So that's going to be. So this is like the I type bit. Yes. So that's going to be in instruction. Well, let's just see if this works, right? So the first instruction is going to be with a func 7 of 0, because I don't know also is add. So func 7 of 0. And then rs2 is, okay, hold on. I gotta think about this for a second. If only I could type this in binary. Verilog binary immediate. Numbers in Verilog, yes. Yes, okay, I know how this works. Binary, yeah, I know how binary works. How do I... Yes, okay, I got it. Binary in Verilog. Wire, register logic. How do I set an immediate value to it? Sign 32-bit integers by a single quote followed by a letter. Ah, single quote, okay. Single quote B. And now I type out my thing. 1, 2, 3, 4. Hold on. Cool, that makes sense. Close all of that. Down here. Func 7 is 25 to 31. Hold on, let's count down. 31, 30, 29, 28, 25, 20. 31, 30, 29, 28, 27, 26, 25. Cool. So for RS2, let's go into 1. So this is going to be 1, 2, 3, 4, 1. RS1, let's go to 2. 1, 2. Cool. And then for Func 3, it's 0 for add. So first instruction is going to be add. So 1, 2, 3. Destination register, let's go to 3. So 1, 2, 3, 1, 1. Hold on. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 1. 1, 2, 2. I probably had spaces. 1, 2, 3, 4, 5, 6, 7. Space. 3, 4, 5. 1, 2, 3, 4, 5. I'll remove the spaces at the end. 1, and then it's going to be func 3. 1, 2, yep, and then RD, and then the opcode is 0, 1, 1, 0, 0, 1, 1, 0, 1, 1, 0, 0, 1, 1. So it's going to be adding those two registers together. And let me just delete some of these. Paste this in. Cool. And so, I don't know. So let's add register 1 and 2 to get to register 3. Then let's add register 1 with itself. So let's add register 1 with 3. And write that into register 1. Yes. And then there we go. There we go. Cool. There is background noise. I do not particularly want to end the stream here. So I will keep going in spite of the background noise. Cool. So yeah, now we had to have it honestly. And let's throw in an add immediate instruction. So let's just set this as the first instruction we do, which is an add immediate instruction. So the opcode is just we get rid of this one and replace that with a 0. Then zeros for func 3. So already let's just write it into the first register. Right, so this one's gonna be an add 0, whatever. Yeah. And then we're going to go func 3 is 0. Func 7 is not a thing because it's immediate. Yep. So I should probably, there's the 12 bits there. And RS1, the source, right, so because we're adding it, is going to be 0 because we're adding it to x0. And the value we're going to put into register 1 is, I don't know, let's put it in 15. I like 15 as a number to put in. Cool. So just let's see if this compiles. If it doesn't compile, then we're cooked. But spaces should hopefully be fine. Yeah, so then we have the clock, we feed in the instruction. Cool. We need to create, let's just see if this compiles. / compile. Error in registers. Okay, let's go through registers now. 11, 15. Okay, so 11. Wire, we don't have any wires there. Fair enough. What's next? 14. Syntax error. Okay, line 14. Always at positive clock edge. It's because I forgot a semicolon. CPU. Invalid module item 15, 19, and 16. 15. Invalid module item instruction decode. 19. And hold on. 19 is syntax error. Probably because I forgot a semicolon. Yep. And 16 for what? 14 I have syntax error. Oh, because I forgot a semicolon. Let's see if that fixes the other problem. 14, syntax error and invalid module item. Cool. So we have instruction as the input, and our outputs are going to be func3, func7, rs1, rs2, rd, opcode, and a clock. Hold on, what's in our instruction decode? Instruction func3, func7, rs1, rd, opcode, and clock. Okay. Syntax error. What is the syntax error here? Decode ID. We have the instruction. We have func3, func7, rs1, rs2. These are the all outputs. rd, opcode. What is the problem here? I don't get the problem. This is very strange problem we have going on here. Yeah. CPU.v, syntax error, invalid module item, syntax error, malformed statement. Okay, I don't care about that yet. Syntax error in the CPU. What is the syntax error? We've set these val A, val B, val right. Val A, val B, val right. Hold on. So we have this as the decoded instruction we have going on here. Sorry, this isn't the pipeline CPU yet, but you know, we'll get there. Instruction, func3, func7, rs1, rs2, rd, opcode, clock. So we have an ALU, which has val A, val B, func3, func7, val right, clock. So this all takes in a clock, right? And so, yeah, this is strange. Because I don't know what's going on here. What is this? Where's the syntax error? Let me add a space in between here. Line 16 is the problem one now. Line 14. Oh, this is the one with syntax error. Probably because I can't have just one here. Okay, well then I'll just have wire right back. I found the syntax error. Yup, that was a syntax error. CPU test bench. Yup, that was dumb syntax error. So we have a CPU test bench. I should probably find out where the error is, though. 8. Yup, there's... Can't be doing nonsense like this to make my reading job easier. Yup, this is truly what you guys came here to see. Compile. Port 7 registers 1 bit. Warning in line 14 of CPU.v. Line 14. Oh, this should be, what is this? Write enable, yes. Write enable should not take a whole bunch. Hold on. Registers. Hold on. So we're going into registers. Write enable should just be a wire. Why is it taking multiple? If write enable, I should not do an equal to 1. Write enable registers expects 1 bits, got 32. Ah, so pruning it, yes. So nvim cpu.v, cool. So because this is 32 bits. Come on. Okay, whatever. We ignore this. 3 is 0, 7, 0, 3, 7. Okay. At 7, it goes to XXX, no input high impedance state. I don't know about that. Whatever. Whatever. 3, instruction decode.v. Yeah, cool. I need a mux. Yes. nvim, hold on, cpu.v. I will just like manually put this in here. We will set out a mux. If, not opcode, is it? It is opcode. Opcode of opcode of 6. So if opcode of opcode of 7, yep. 0, 1, 2, 3, 4, 5. No, opcode of 5. Then if it's 1, what we do is we set the val A going into the thing. Hold on. So we're going to have val A wire. And what we're also going to have is a, what's its name? A in A wire. And an in B wire of the same width. Not in B, just an in A wire. And for our ALU, instead of val A being our input, we will have in A. Cool. So if opcode of 5, in A is going to be val A, else the in A is going to be the concatenation. Hold on. How to do concatenation in Verilog. Verilog concatenation, yes. Can I see it? It's curly braces, yes. It is, in fact, just curly braces. Nice. It's curly braces with, let's go back to the RISC-V card. It's func7 and rs2. Func7, comma rs2. Cool. I probably set these at the right size. Yeah. Instruction decode, yeah. So width I don't actually care about anymore because I'm just doing 32-bit RISC-V. So output from 3 to 0 is func3, and then from 7 to 0 is func7, and the opcode, because the opcode is also 7. And then the output from 4 to 0, because it's 5 long, is rs1, rs2, and rd. Delete that. y3j, y2j. Paste it in here, and let's just set this to be registers. Reg, reg, reg. Cool. There we go. Now if we go into nvim registers.v, we're gonna keep iterating here. Out A, out B, yeah, that should be a width. Input reg A, reg B, this is where we edit it. So y, yes, data write should also be there. So now I'll just set it here. Input of our, this should be 5 long. And so that's going to be reg A, reg B, reg W. And obviously data to write is going to keeping the same. And we have a clock and write enable, which are just single inputs. And yep, the output is, yep, full width. And registers a full width, yep. And then we nvim our ALU.v. And so in here, input data A and B are correct. And then input, and it goes from 2 to 0 for func3, because it's 3 wig. Input 6 to 0 for func7, because it's 7 big. 6. End. Func7. And then we just remove them from here. And I should probably fix it in not registers, instruction decode. Yep. So instead of 3 here, there should be 2 and 6. And same here, 2 and 6. Cool. CPU.v. Cool. And then in here, we go wire of size 3, 2 to 0, func3. And then size 7, func7. Then of size 5 is going to be our very nice friend rs1, rs2, and rd. And obviously opcode is here too. Cool. Those should be correct. In A should also be correct because that's just based on width. And cool. And in A is set to that. Amazing. And yes. Compile. Yes. 33 has a syntax error. This checks out because I forgot a semicolon. Registers 8 and 7. Registers.v 8 and 7. 8 and 7. It's because I forgot a very nice semicolon. Cool. Warnings. Register A of registers got 5. Expected 6. Sorry, expects 5 got 6. Okay, it's a problem in CPU.v. Okay, did I write 3? No, yep, this is supposed to be a 4. Let's just compile. Yep, again, problem. Write enable expects 1, got 32. That we deal with. Instruction of instruction decode expects 1, got 32. That's a problem. Instruction decode should be full width, yeah. What? In A is not a valid L value. Okay, that's whatever. No, it does matter. We just need a mux. Okay, I'll just manually create a mux then. nvim CPU.v. I'll just manually do a mux then. In A is set to val A and what is the thing we're checking for here? Opcode 5. Val A and opcode 5 plus not opcode 5 and this. Compile. Okay, what's the problem here? Unable to bind with dimension must be constant. Huh? Dimension is constant, 32. Oh, this. Mux Verilog. We're googling now. 4 to 1 mux. Sorry, we need a demux. We need a demux. No, we do need a mux. Yes. Input out. Oh, it's just variable question. Okay, it's sure then. It's a ternary operator. Question mark. Val A or colon. Sure then. Okay, error. In A is not a valid L value. In A is declared here as a wire. Okay, well, let's just set it to be equal to. Okay, sure. Amazing. We have a mux. How do I just like... in A should be a register. Where is in A? Instead of a wire, there should be a register. And then problems go away. Cool. Warning. Port 7 expects 1 bit, got 32. Because that I said a hard value, whatever. Instruction expects 1, got 32. Instruction decode. How is instruction input with... Oh. There we go. 32-bit. There we go. Cool. Test. Finish. Cool. NVIM CPU test bench. And then now let's just oh no, CPU.v. Now let's just modify the output. Output should not be val right. Output should be in A. So the value that we're feeding into the input. / compile / test. We are not changing NVIM. Okay, hold on. Let's edit the test bench. Instead of this being 2, I don't know, let's set it to... Let's give the CPU 10 cycles to fix itself. Right? 10 cycles. / compile / test. It's 15. This is good. 15, 0. What are we? We're trying to feed in 15, yes. Cool. So we have that correct, which is a very good sign. Actually, very, very good sign. Now, what we need to do, we have to keep going. We have to edit out, yeah, so nvim cpu.v. Cool. So what next output should be, no, in A is the output. Cool. So then val write should be I should just do .compile and test. We're not writing to anything. Well, we're writing 0. Cool. Yeah. So now what we have to do is we just have to keep. We gotta kind of keep thinking about this a whole lot more, right? Like, that's the hard part here, is the thinking. Thinking is the hard part. So yeah. So nvim cpu.v. Yes. Yes. Okay. So in A is correct. What about val b, which is here? It's always 0. Yes, that checks out. No, it never gets set to something that isn't 0. Yes. Registers.v. Val b should be set to value in x1. Just set the default value to 0. Yep. Output is 0. Is nothing. Okay, hold on. Now we're dealing with all of the issues, you know? We're running face first into every single one. nvim ALU.v. Okay, what is the output here? The output is either adding or subtracting. Okay. Func7 is either 0 or 32. Func7, I just make sure it's 0 for all of them. CPU. Hold on, let's just output func7, right? So we should make sure that all of these are 0. Out func7. Func7 gets hold on. nvim CPU testbench.v. Instruction, I'll set the default value to 0 so that, you know. Hold on. At time 0, 1, 3. Oh, it changed at 3. Yes. Because it's feeding in all zeros. And it's not updating. Okay, so this means that func7 is always 0, which checks out. What are we changing here? Let's see what RS1. Let's see if our RS1s are in fact correct. And it's whatever. So you should expect it to be 0, right? RS1s. Yep, it should be 0 for the first one. Yep. Then it should be 2 and 3. Yep, checks out. Takes 3 seconds to update. Checks out. Then what we do is let's check if our destination register is good. Destination register is 0. What? Oh, we're trying to write to 0. That's what we ignore that. 1, 3, 2. Okay, we're trying to write there. Okay. So the destination register is correct. Val write. What is val write? The value of writing from our ALU is 15 at that point. Yep. Cool. Then, because we're trying to write 15... Oh, does it get set to 0? Hold on. It might straight up get set to 0. Like, immediately after. So... I should probably store it in a register. Or... val write. Register. Val write. No, that should not be a register. registers. We should set this to a 1 when we get to... I mean, we're just letting it feed through, and just the clock is just like cycling it through, right? So instructions should be correct. What if we're getting into cyclical writing? But here, in the first case, it should be fine, right? So it should be set to 15. Yeah. Okay, very strange set of outcomes. Very, very strange set of outcomes. Yeah. Cool. I just had to keep figuring out what is going on here. Yeah. Yeah. Okay, how am I gonna do this? How am I gonna do this? I don't know. I think my brain is tapped for today. I have 2 consistent viewers. That's fine. I will leave it as is. I will see you guys all next time. And I'm ending stream here. Goodbye.